Hola clase. Today we are going to see how to approach optimization problems. And for us to be able to do this, there are a couple of things that we need to know. Let's see if we can do it in one screen in less than 10 minutes. It's going to be tight. First, you're going to need to know how to form expressions, because optimization problems are always going to be word problems. Then you need to know how to derivate polynomials in our case. And lastly, you need to be able to find and evaluate stationary points. And if you think of it, it's because optimization problems, you're trying to find the maximum or minimum of something, of some amount. And you know, if you had a graph, that those are these points in here, points where your gradient is 0. So your objective is to find these ones and pick the one that works for your word problem. Okay, how to do it? The first step, you need to identify the element that you want to optimize. What are you searching for to make maximum or minimum? And once you have it, you need to find a function of it, an f of x for it, only on one variable. Once you have it, you can derivate and make 0. Because again, remember, you're searching for the stationary points. Once you've got it, you can evaluate your stationary point. And I'm putting this as an optional, because generally your context is going to tell you if you are here on a maximum or here on a minimum. But we're going to put it as a step. And once you've got it, the important part, you could give a solution. Okay, let's see this in an example. They tell me here that I've got a rectangular box, it's closed, and they're telling me that the length, it's twice the width, so I can put them in relation of x, and it's got a surface area of 300 centimeters square. Of course, first step in any word problem is draw and label. I've already done this. And they want the maximum volume. All right, this is my first step. This is what I'm going to want to make maximum. So I'm going to have to find some type of volume in function of x. That's my objective. Okay, everything that I do, it's going to go to find this, and this is the hardest part. Right, I know that maximum volume, then that's going to be when dv over dx equals 0. And I'm going to find what I've got for a volume of a cuboid, a rectangular box. Length times width times the height. And now this is a problem, because I've got two variables and I need only one. I need v as a function of x. So I'm going to have to figure out a way of link it. And for that, I've got this number here. I've got the surface area. So I know that the surface area is 300 centimeters square, and I can find this in terms of x and h, because if you think of it, I've got 2 of these sides, which are 2x squared, and then I'm going to have two of these faces, xh, and two of these faces, 2xh. So I can say that the whole surface area is going to be 4x squared plus 6xh. And now I'm going to be able to make h in terms of x. So I'm just going to simplify here. I'm going to divide everything by 2. And now I'm going to leave h alone. So this is going to be 150 minus 2x squared over 3x. And the beauty of it is that then I can come here and substitute, well, let's actually be tidy. Substitute the h for its equivalent, this expression here. So I come in here, 150 minus 2x squared over 3x. I'm just going to simplify in here. That's going to give me 100x minus 4/3 of x cubed. And now that I've got v of x, volume only in terms of x, I can derivate. And that's a polynomial. So this is going to be 100 minus 4x squared. Now this is the easy part, because now we're already here on step 3. The expression is out of the way. The rest is just a bit of math and rearrange. I'm searching for a stationary point, so I'm going to make this equal to 0. And now I can solve for x. This is going to be 100 over 4 plus or minus the square root of that. And now, this is the part that I was telling you. The context will tell me which one it is. Because if this gives me plus or minus 5, well, I know it has to be this one. It has to be a positive, because it's a length. But let's say that we want to try and prove it. I'm going to have to scroll out. Then we're not going to be trying to evaluate looking a bit below and a bit above. We're just going to do second derivative, and that is minus 8x, which means I can easily evaluate. I can go, okay, which is the second derivative when x equals minus 5? Well, if I do that, that gives me 40, which is bigger than 0. And remember, I'm only interested in the sign. And I go, okay, which is the second derivative when x is actually 5? That gives me minus 40, which is smaller than 0, which means I've got a local maximum, which agrees with what we already knew, positive length. All right, we've got the number. Now we just need to actually give a solution, because that's going to mean that then x equals 5, but they want the whole dimensions. 2x equals 10, and h, remember I've got an expression for h, so I'm just going to substitute 150 minus 2 times 5 squared over 3 times 5, and that gives you 6.6 periodical, or if you want 6 2/3, and they want the dimensions, So I just need to give the answer. Box is 5 by 10 by 6.6 reciprocal centimeters. These are the dimensions. I answered what I wanted, box it, and I'm done. Okay, now it's your turn to go and practice. Thanks for watching.